This is a talk that was given at Photonics West on January 21st, 2026. Silicon Light Machines has been making spatial light modulators for over 30 years. Today I'll talk about some of our latest developments aimed at the laser processing space. So this talk is on going towards higher throughput laser processing via high-speed beamforming and patterning. Lasers have become essential to modern manufacturing because they deliver energy with high precision and enable processes that would be impossible with conventional tools. In many processes, we have a desire for higher throughput and precision, and we know it's not as simple as just putting more laser power onto the part to get more throughput. The process usually doesn't scale linearly, and we often begin damaging the sample as we increase the power. Another issue is the quality of the finished product. Gaussian beams are the simplest to work with, but for many applications they don't give the best result. I'll be comparing to conventional or single spot systems, and this is what I'm talking about. We have a laser beam that gets resized and goes through a galvo scanner that can scan the angle in 2 dimensions. It then goes through an f-theta lens, which is chosen to give the spot size, scan field, or other parameters that we need based on the application. Some of the limitations are that it's a single spot, when we know multi-spot systems are possible. The galvo speed is limited, and those limits tighten as we demand higher positioning accuracy. The beam shape is static when we might want to change it throughout the process. And we have a trade-off of resolution by using a smaller spot and throughput by using a bigger spot. I want to dig into that trade-off a little bit more. Typically when developing a process with a pulse laser, we run tests with different fluences and pulse overlaps or scan speeds to see different results. Once we settle on these parameters, the laser power is pretty much set. So this chart shows different spot sizes with some reasonable values chosen for fluence and overlap. And the max scan speeds are scaled from the ExcelliScan scanner by ScanLab using a 23 micron spot size. The power that we can use at higher resolutions is quite small, only half a watt for 10 microns and just 7 watts for 40 micron beam. But much higher laser powers are available. In fact, this graph from Coherent shows that ultra-fast lasers become much more cost-effective as we go towards hundreds of watts. So there's an opportunity here for high-speed beam shaping to be applied to allow us to use those higher-powered lasers. We can distribute the light to make use of higher powers and select non-Gaussian beam shapes that result in a better process. With real-time pattern control, we are free from constraints of static or slow beam shapers, and we can even use feedback from the system to determine what the next beam shape should be. So today I'll talk about how we can address this opportunity with spatial light modulators. But in order for a spatial light modulator to help with this, it needs to be very fast, like microsecond switching times, and capable of handling high laser power. We'll talk about 2 kinds of modulation, amplitude modulation and phase modulation. For amplitude modulation, we'll talk about the planar light valve, or PLV, in our Katana system. This is a 2D array of elements with grayscale attenuation control. The device we'll show today is wired to give modulation in one axis. The amplitude pattern on the PLV gets directly imaged to the work surface, so you can think of it like printing with light. You can see the array of dots pattern below, but it can be any arbitrary pattern. For phase modulation, we'll talk about the displacement phase modulator, or DPM. This is a 2D array of elements with analog displacement control. It can be programmed with any phase pattern we like to create the desired profile at the output. Both devices are programmable, have high switching speeds, and capable of handling high laser powers. First, let's dive into the Katana and the PLV. This is a very high-level overview of how the PLV works. In the bottom, you can see a microscope image of the surface structure. It's made up of round discs which are active and move up and down, surrounded by a static faceplate of about the same area. With no deflection, the device acts as a mirror. When voltages are applied, the discs deflect downwards to create a diffraction grating, diffracting light into well-defined orders. The amount of deflection is set pixel by pixel. On the right side, you can see how this might be used in an optical system. The illumination light is not shown, only the reflected light. The light goes through the first lens, and each diffraction order is focused to a tight spot. An aperture is placed to only allow the 0th order through, which gets re-imaged by the second lens. In this way, the deflection of the active disks becomes an amplitude change at the image plane. And here are some measurements. On the left, you can see the intensity versus voltage response of a single pixel. We can choose any point along the curve and are often interested in using the bright and dark rollover points. The ratio of these is the contrast ratio, which can be very high, over 100 to 1. On the right side, we see how fast a pixel can switch between the bright and dark state. The rise and fall times are under 1 microsecond, which allows for hundreds of kilohertz refresh rates. This PLV is used inside the Katana system, which is a full solution that incorporates all of the optics needed to take advantage of the device. The head takes a Gaussian input beam, in this case an IR laser that can be pulsed or CW. The beam goes through the illumination optics, which shape it into a rectangular top hat that matches the device area, and then it goes through the imaging optics, which project a demagnified image of the device onto the work surface. There's an integrated galvo scanner to scan the output beam. The output is a programmable line beam, which is top head in the modulated direction, and a sync squared profile in the focused axis. We've discussed this system before, and you can search for planar light valve optical head to learn a lot more about it. We've made several advancements over the last year. The projection optics have been redesigned to create a larger 50mm scan field with a 20 micron resolution. We've created a new controller that we call the streaming controller. It has dual memory banks so that we can upload data even as it's being read, allowing for continuous pattern streaming. So loading patterns adds very little overhead to the process. And we've demonstrated on-the-fly galvo and stage synchronization, which allows us to process very large areas more quickly. This video demonstrates the larger galvo scanning field, which is about 1.8 times faster than when we use stage scanning. The larger spot size also gives an increased depth of focus, which has resulted in better process uniformity across uneven surfaces and requires less critical sample positioning. This image is made up of millions of patterns on the PLV, and the streaming controller allows it to run continuously. And this is a demonstration of on-the-fly writing, which requires synchronization of the PLV, the galvo, and the stage. This work was done by a laser tool manufacturer named Tete Laser. The stage is moving from left to right while the galvo scans the beam up and down. The actual scan path is then a diagonal line, and this is taken into account when creating the image data. Using this method, the width of the scan field can be expanded to whatever amount of stage travel we have. Next, I'll show some black marked images on stainless steel that highlight the precision of the system, though it can also be used for engraving or anything else that you do with an IR laser. This is a resolution test pattern which was marked by scanning vertically and modulating in the horizontal direction by the PLV. The section labeled 08 shows 20 micron spots which are well resolved, and even the 10 micron spots below can be distinguished. And here are some larger images with very fine details. Compared to conventional systems, the appearance of the surfaces processed by Katana tend to show a more uniform color. Katana really shines when we need a high throughput and high resolution. This graph shows Katana's throughput gain using power delivered to the workpiece as a proxy across different spot sizes that approximate resolution. For lower fluence applications with small spot sizes, we can utilize 30 to 100 times more laser power than a conventional system, which we've demonstrated in previous benchmarks. At higher fluences or larger spot sizes, the difference is less stark. But even at 40 to 60 microns, some large gains might be available. And next we'll talk about our phase modulator, the DPM. The DPM has the same underlying flexible membrane as the PLV, but the top layer was changed from active disks to fully active squares, so the entire surface moves. Each square pixel is simply displaced, which creates a localized phase delay on the wavefront of that pixel. It maintains the high speed and power handling characteristics of the PLV. The device we'll show today has 8,000 pixels arranged in an array of 32 by 256. It allows for full 2π phase modulation up to 532 nanometers. This is our first demonstration of DPM technology, but we do have a device with 16,000 pixels arranged in a square array coming later this year, which will handle much higher laser powers and work with 1064 nanometer lasers. So why is phase modulation exciting? Traditional optics can be represented by their phase effect on an incoming wavefront, so we can simulate many optics by programming their phase representation into a phase modulator. We can also use holographic data to create arbitrary intensity patterns in 3 dimensions. Diffractive optical elements can be used to create many unique beam shapes. Like if we want to convert a Gaussian beam to a donut profile, a DOE works great. But we might want an asymmetric profile like this shifted donut that was found to create very uniform melt pools in additive manufacturing. We'll need the direction of the high-intensity edge to change with a scan path, which cannot be done quickly with a DOE or LCOS modulator. In this case, we can introduce the DPM to change the beam profile during a scan vector. This simulation shows a shifted square beam that scans over a circular path. And here's an actual camera image taken while the DPM is steering the beam in a spiral. Below the camera image, you can see the phase pattern ranging from 0 to 2 pi that was applied to steer the beam. And here's another demonstration that modulates the beam at up to 250 kilohertz. So depending on the rep rate of the laser, a different pattern could be used for each pulse. In the top left, you can see a donut beam that expands and contracts. As it goes to a higher speed, it eventually gets so fast that we can no longer see the changes, just an integrated intensity pattern. The video on the right shows a donut beam with an offset center, and the pictures on the bottom show some other beam shapes that we've created, like a square top hat, a ring, and an array of spots. In terms of system integration, it's relatively easy to incorporate the DPM into a conventional system. We would add some beam shaping optics to create a beam shaped for the DPM and place the DPM before the galvo scanner. Now some thoughts in closing. When we talk about high power, this is what we mean. The PLV has been stress tested the most, and it's shown good performance for thousands of hours at over 700 watts of laser power. It's been used for extended periods of time with pulse energies around a millijoule. The DPM has undergone short-term LIDT testing, and we use ratios to estimate what the current DPM device and the next generations can handle. We're looking at multiple kilowatts of power and millijoules of energy for our next generation devices coming later this year. So I hope I've shown some of the benefits that SLMs can bring to your laser processing, but they're not needed for everything. First, you'd want to ask yourself if you have one of these pain points. Do you need better throughput, quality, or resolution? If yes, could a static beam shaper or slower LCOS SLM fit the application? If the speed and power handling of our SLMs are needed, then we'd look for a DPM or PLV solution. This is a very high-level breakdown, and there are many applications that could benefit from either of these devices. But in general, the Katana with the PLV is better suited when very high image quality is needed, the image is dense, and a lot of excess power or energy is available to be used with the elongated line beam. The DPM excels when a higher intensity or fluence is needed, or a complex beam shape is required, and it results in a more compact system. To conclude, our high-speed MEMS SLMs are transforming what's possible with laser processing systems. We've shown systems making use of amplitude and phase control. With the Katana, we've shown the recent advancements, and with the DPM, we've shown dynamic high-speed beam shaping. Both systems are very robust and built upon over 30 years of industrial MEMS technology. The main takeaway is that the control they give us allows for simultaneous gains in both throughput and feature quality. So thank you for your attention. Please come visit us at booth number 4640, and you can see live demos of all of these products.